What specific problem does AgentTorch aim to solve in the context of agent-based modeling, particularly regarding scalability and agent expressiveness?
AgentTorch aims to address the limitations of traditional agent-based modeling, ABM, by enhancing scalability and agent expressiveness. Specifically, it enables the simulation of millions of agents on commodity hardware through vectorized computing, significantly improving computational efficiency up to 40,000 times faster than traditional frameworks. Additionally, AgentTorch allows for the incorporation of large language models, LLMs, as agents, which enhances the expressiveness and adaptability of agent behaviors, enabling them to better capture complex dynamics such as individual responses to environmental changes. By utilizing LLM archetypes, AgentTorch can efficiently scale simulations while maintaining the fidelity of agent behavior, thus overcoming the challenges of querying LLMs for each individual agent. Overall, AgentTorch facilitates the creation of more realistic and scalable ABMs that can effectively inform policy design in complex systems.
How does the proposed method work? Illustrate the main steps of the AgentTorch framework and the integration of LLM agents within it.
The proposed method AgentTorch operates by enabling the scalable simulation, calibration, and analysis of agent-based models, ABMs, with the integration of large language model, LLM agents. The main steps of the AgentTorch framework include, first, defining the agent and environment dynamics, where agents update their states based on interactions and environmental factors. Second, utilizing LLMs to inform agent behaviors by querying them with contextual prompts that include demographic and environmental data, allowing for adaptive decision-making. Third, employing archetypes to reduce the number of LLM queries needed, thus enabling the simulation of millions of agents efficiently. And finally, calibrating the model using gradient-assisted techniques to ensure that the simulated outputs align with real-world data. This framework allows for the execution of complex simulations, such as those modeling the COVID-19 pandemic, while capturing the nuanced behaviors of agents in response to changing dynamics and interventions.
Can you provide a simple illustrative example of how LLM agents interact within the AgentTorch framework? Walk through an example scenario detailing the mechanics of agent interaction and decision-making.
In the AgentTorch framework, LLM agents interact by utilizing prompts that incorporate both demographic and contextual information to inform their decision-making. For instance, consider a scenario where an LLM agent is tasked with deciding whether to go to work during the COVID-19 pandemic. The agent's prompt might include its age, sex, location, current disease dynamics, e.g., number of new cases, and any financial stimulus received. The LLM processes this information and outputs a probability for the action, "Do you go to work?" based on the provided context. This decision-making process is executed through the agent's update rule, where the LLM output is used to determine the agent's willingness to work, which is then sampled from a Bernoulli distribution to simulate the agent's behavior. By aggregating the decisions of all agents, the framework can capture population-wide behaviors, such as labor force participation rates, and analyze how these behaviors adapt over time in response to changing circumstances, such as the decline of stimulus payments or the emergence of pandemic fatigue. This illustrates how LLM agents can effectively model complex interactions within the AgentTorch framework.
What are the advantages of using the AgentTorch framework compared to traditional agent-based modeling approaches, specifically address improvements in simulation speed and agent expressiveness?
The AgentTorch framework offers significant advantages over traditional agent-based modeling (ABM) approaches, particularly in simulation speed and agent expressiveness. Firstly, AgentTorch leverages vectorized computing, enabling the simulation of millions of agents on commodity hardware, achieving speed improvements of up to 40,000 times compared to traditional object-oriented frameworks. This scalability is further enhanced by the use of archetypes, which allows for efficient querying of LLMs, thus preserving computational gains even with LLM-informed agents. Secondly, AgentTorch facilitates the creation of more expressive and flexible agent architectures by allowing the integration of neural networks and large language models, LLMs, which can capture complex behaviors and adapt to environmental dynamics. This expressiveness is crucial for accurately modeling individual behaviors in response to varying contexts, such as demographic factors and disease dynamics, thereby improving the realism and utility of the simulations for policy design.
How was the effectiveness of AgentTorch validated in the experiments? Discuss the datasets used, experimental design, and metrics for performance evaluation.
The effectiveness of AgentTorch was validated through a series of experiments focused on simulating behaviors related to isolation and employment during the COVID-19 pandemic in New York City, utilizing a synthetic population of 8.4 million agents initialized with census data. The experimental design involved querying LLMs with different prompts that included demographic attributes, disease dynamics, and financial incentives to assess their ability to recreate population-wide behaviors. Performance evaluation metrics included the correlation of LLM agent outputs with real-world data from the U.S. Bureau of Labor Statistics, which demonstrated that the correlation improved as more contextual information was added to the prompts. Additionally, the study compared the performance of different agent architectures, heuristic, archetype, and LLM agents by calibrating structural parameters to historical time series data of infections and unemployment rates, ultimately finding that archetype-based models achieved the best performance. This comprehensive approach allowed for retrospective, counterfactual, and prospective analyses, showcasing AgentTorch's capability to capture adaptive behavior and inform policy design effectively.
What were the main findings from the experiments conducted with AgentTorch, particularly regarding LLM agent behavior and its implications for large-scale ABM research?
The experiments conducted with AgentTorch revealed that LLM agents can effectively simulate population-wide behaviors, such as isolation and employment, with high correlation to real-world data, particularly when provided with contextual information in prompts. Specifically, LLM agents demonstrated the ability to adapt their behavior over time, capturing the effects of pandemic fatigue and changing economic conditions, which is crucial for realistic ABM simulations. The use of archetypes allowed for scaling simulations to millions of agents while maintaining computational efficiency, as querying the LLM was limited to unique combinations of agent characteristics rather than each individual agent. Furthermore, the results indicated that archetype-based models outperformed LLM agent models in terms of calibration accuracy, highlighting the trade-off between agent expressiveness and simulation scale. Overall, these findings suggest that integrating LLM agents into ABMs can enhance the modeling of complex systems, but careful consideration of agent architecture is necessary to balance fidelity and scalability.